Okay, you can go to the next slide. This is just something on myself. I'm an infrastructure guy. I'm from the overhead contact lines, so mechanics. It's not ICT. It's a lot of energy. It's dangerous. Okay, and involved in many projects. Yeah, next please. I can see it's not very readable. We have two problems, challenges, legal challenges and technical challenges. We have, of course, the TSIs and parts of the European standards referenced in the TSIs. And, of course, the RINF. These are legal requirements. And then we have some far more detailed and elaborated standards from UIC, very old leaflets, new standards, revised standards, and even on IEC level, of course. So, but these documents are not written for trains with onboard energy storage batteries, for example. And that's a problem. Next. So we try to tackle this in two ways, the legal problem and the technical problem. On the left-hand side you can see that we started early this year in March with a new, let's say, ad hoc joint task force from the infrastructure managers, EIM and CER, and of course CER is also integrated companies. Eptola is also represented, and NB Rail. And then you can see some companies who are actively involved in trying to solve the legal problem. Unfortunately, Unife did not yet participate. There is clearly interest from them, but they judge it too early. And then on the technical level, there's a new working group 25 trying to develop a new technical specification for Senelec. And this is about, it's not the same scope. This is about infrastructure, because before it was stations, and for dedicated contact line sections. So you can go to the next slide. I will show some examples of these Senelec solutions. Yes. Next, please. Yeah, it's more or less the scope of the standard. So you can have modified existing OCL systems to charge the train, which will not necessarily be TSI compliant, but they will use the power supply from the existing systems. Then you can have, let's say, large new island sections. This means this is a new electrification. This is completely TSI compliant, but it's another start for a new network. Then you can have some medium islands, not TSI compliant again, and then the short one, which is on the picture, nice picture from a German town, Tübingen, where you can see just, I know if you could, there's no pointer, but this is just a few meters of overhead contact line, a rigid one, and then another one over there, so you have two ones, and that's it. That's a very short island where the train, this is obviously a battery train that can charge. And here you can see the substation. This is a substation connected to the city grid. Yeah, that's technically, but it's all about overhead contact lines, nothing else. Next. Yep. Then back again to the legal problem and the task force for change request 350 on the TSI, not only TSI Energy. We had a key objective on the, of course we want to support the Green Deal, everyone wants to support the Green Deal. Short-term objective that was to allow full charging of trains, and there was a main problem that's current at standstill. If you want to charge battery trains by the most obvious thing, that's the pantograph on top of it, of the train, then in the previous DSI there was only a requirement for the old trains to charge for DC systems, and so we opened it up for AC systems, but the final proposal is still to be discussed within ERA. We were in a hurry, we introduced it in April already, but as you all know, TSI will be revised next year, and there is a process to be followed, so it's still under discussion. I hope we can open it up for the battery trains that we can charge them at standstill more easily by the pantograph. And then you have the more long-term objectives for Not TSI 2022, but the next TSI afterwards. Yeah, next please. But first we need to know what the trains want. Because we can build a lot of infrastructure, but if you do not know what the trains want and need as battery power, then you know. So we all know the picture I showed is a BMU, a battery EMU, so with 2 megawatts or something around that. But there are other examples with up to 5 megawatt of batteries. This is within a special tender. And this is an example for a Norwegian very long railway line where we can reduce electrification up to less than a third of the total length of the line if we could use these battery trains, which obviously would reduce enormously the infrastructure cost. Okay, thanks. That's next, yes. But then we run into trouble in the existing legal documents because there are some things written that energy, so the overhead contact line has no problem feeding a train up to 2 megawatt. We do not, trains up to 2 megawatt, they do not need a power or a current limitation. Because we said there is a direct link, the overhead contact line is able to provide that power easily. No problem. So we wrote that in the TSI. And that's the definition also. You can see that the scope is limited to the contact line system, okay? By using pantographs. I will come back on that later because this 2 megawatt is a problem. We might need power limitation far below that. And then again, the short-term objective that we try to introduce in the TSI is for the current at standstill for DC systems. Now we open it up for AC systems also because battery trains charged under AC systems will need a lot of more energy than the actual trains we know now. Next. And these are all the possibilities. If you can see, all the technical possibilities at best can deliver 2 megawatt of power. They cannot deliver more. You have the current collector, so you have the four target systems. And you can see power at standstill is very limited. So this is about 30 minutes that the train must stand still to charge. And then it can only have 2 megawatt in the 25 kV system. In the others it's less. And then the other solutions is just by a plug. You have the first UIC 552 plug, which is a very old system, a little bit expensive, but nowhere near the 2 megawatt. Don't be fooled by the yellow markings. And then you have an industrial plug, which is used. This should be here in the room also. So these plugs, these are used everywhere. And then there's even a new type of plug. What do we want? We have four charging possibilities. What do we want? What do we want to standardize? We don't know that. Okay, this is an example of such a newer shore supply. And also in Germany, the second bullet, they are talking about a 5th power supply system through the pantograph. So obviously TSI already has 4 existing target systems. We're not going to add a 5th one in the TSI, but it might be a good technical solution. Why not? Why block that? We must be careful to standardize too early and block future solutions that might be interesting. And then you can see, so the plug solutions are only when the train is really stabled overnight. Then these plug solutions have sufficient amount of power to even charge a battery train completely. Next. And I like this picture. We are not standardizing new things. This is a nice tram from maybe 100 years ago, something like that, in Paris. And you can see here a nice charging station and the cable feeding the tram. So, next. Yes, I don't know if the animation works. This is about the second plug solution. So this is an industrial plug, a 400 volt plug, and then you can see, I hope yeah, the message came through. With this system, we can be future-proof for more type of trains, also with fuel cells, for example. That it does not need the traction converter absolutely. So this is maybe more flexible than the UIC 552 plug. Okay, next. This is some standards. Then you can read if you want them. Okay, next. Good. But there are a lot of standards involved, and we are trying to include battery train operation in these standards. Yes, next please, next. Again, to the current at standstill, what we did up till now, there are a lot of tests being done because it's a problem to charge battery trains. You can see there's a recent report from RSSB in the UK. There has been tests done in Germany, in Belgium, Italy, France, etc. And because to charge the battery to the pantograph, we need to know what are the margins. I believe we can provide more power through the pantograph, but the values written in actual documents, TSIs and standards, are of really safe margins. They allow very safe operation of the trains, and I believe it can be higher. So go to the next, then we could see. This is a nice example. You can read all the text, but what they did here, this is something you will never see on the railway lines now. These are two rigid overhead contact beams. One is installed often, in for example, Berlin main station. You can have that, but this configuration would allow easily 220 amps. So this more than doubles the actual requirement without problems, and then we can have a much more power under the to be provided to the trains. Of course, then you have all the circumstances we can with the tests and that differ. Next, please. Yes, this is an example from SNCF, but then again, these are not standard pantographs. This should be allowed to for the battery train. With these pantographs, they are not allowed in many countries, but you can see 1,000 amps. We can provide much more power to the train by that means. Next, just an example. Okay, Belgian examples. So we have the limit here. Then it depends on your national circumstances to which temperature you can go when charging at standstill through the pantograph. So the upper limit is, of course, this is the standard, and then the lower limit, that's you have to calculate for each country. Yeah, next. So this is an example. You can read all the messages, but keep in mind this one. So this is the limit that we can use. We can see it's more than 200 amps, even in really bad circumstances, because this is also a worn contact wire. So there is a possibility to increase the amount of power at standstill. That's the message from these three examples. Next. Then about charging strategies, because we know when a train is at standstill, it can have during a large time a limited amount of power, but during a short time it can have much more power. And then I come to the ICT field. Then we need communication with the trains and infrastructure. We need to know what the state of charge of the batteries is. We need to know which train is going to depart first. We have to know a lot of things, and that's where the ICT comes into play. Yeah, and then of course, another technical. I'm a technical guy. Sorry for that, but we need a train that's just plugs in, let's say, through his pantograph, is demanding on the infrastructure side, and that's why the Germans want to do 50 Hertz on their system. This reduces the inrush current. But of course, all these things are not foreseen, but the standards can do that in future. Next. And this is how it looks like. So you can see clearly, depending on your configuration, this is standard here, 30 minutes. That's standardized. But if we go in short times, 2, 4, 6, then we can provide much more power, and all these values go up, and we can be more comfortable in charging these trains. The next. And then something else. We always talk about batteries, but there are other technologies, so we should be careful, because these technologies allow much faster charging or discharging also. So how do we coordinate infrastructure and the trains? Because there is the 4th railway package. We cannot build an infrastructure for one type of train. We should build it for a range of batteries or energy storages that another train in maybe 10 years' time can also be charged and run the same timetable as the one we had in mind when designing the infrastructure. And that was it. I thank you for your attention, and I think...
No, thank you. Thank you very much, Paul. That was